Two black holes, each dozens of times more massive than our Sun, collided so violently that they tore a hole in space-time wide enough to shake the universe. And we heard it, through ripples in space-time captured by detectors right here on Earth. This wasn't science fiction or some theoretical musing, it was real. On November 23, 2023, our instruments picked up the echo of a cosmic event that occurred billions of years ago. A black hole merger so massive, so intense, it defied nearly everything we thought we knew about how these invisible giants form. The signal, now named GW231123, wasn't just another blip on the radar of gravitational wave observatories. It was the most colossal black hole merger ever detected. One black hole was about 100 times the mass of our Sun, the other around 140. When they slammed into each other, they created a single entity weighing roughly 225 solar masses. To put that in perspective, this new black hole outweighs most previously known ones by nearly double. That kind of weight doesn't come easy. According to current models of stellar evolution, stars that massive should shed their outer layers before death, preventing the formation of such heavy black holes. This phenomenon, known as pair instability, makes the existence of GW231123 deeply puzzling. Scientists suspect a deeper, messier history. Maybe what we saw wasn't just a one-time crash, but the result of an earlier series of mergers. Think of it like cosmic matryoshka dolls, small black holes merging over eons, stacking mass until eventually reaching this record-breaking scale. If true, this would mean that black holes are more socially active than we thought, living not in isolation but in chaotic neighborhoods filled with gravitational drama. And if the mass wasn't baffling enough, their spin was. These black holes weren't tumbling lazily through space. They were spinning near the physical limits set by Einstein's theory of general relativity. That kind of spin isn't just a technical detail. It dramatically affects the gravitational waves we detect, warping the signal into something almost impossible to decode with current models. Gravitational waves are the ripples these violent events send through space-time itself, traveling vast distances until, with delicate precision, they're captured by instruments like LIGO in the US, Virgo in Italy, and Kegra in Japan. These observatories, together forming the LVK collaboration, use high-powered lasers and kilometers-long vacuum tubes to detect shifts smaller than a proton. When GW231123 hit, it stretched and squeezed space-time in just the right way to trip our sensors. But the signal wasn't clean. It was twisted and distorted, tangled by the rapid spins and massive size of the merging black holes. To make sense of it, researchers had to call in heavy-duty theoretical models, including simulations of relativistic spin dynamics that are still being refined. The whole ordeal is forcing physicists to upgrade their tools, both computational and conceptual. Even stranger, some scientists aren't entirely convinced that what we observed was a plain and simple black hole merger. The shape and intensity of the signal leave room for more exotic interpretations, perhaps a collision involving primordial black holes, or other exotic compact objects predicted by alternative theories of gravity. The signal might be hiding clues to new physics. This is what makes GW31123 such a landmark discovery. It's not just big, it's weird. And in science, weird is gold. For now, the leading theory holds. Two extremely massive, fast-spinning black holes collided, releasing an enormous burst of energy in the form of gravitational waves. The ripple arrived billions of years later, during the LVK's fourth observation run, and was picked up thanks to improvements in sensitivity and coordination across the global network. The data will be made public through the Gravitational Wave Open Science Center, allowing physicists around the world to join the puzzle solving. Meanwhile, the LVK collaboration is preparing to present their findings at the GR Amaldi meeting in Glasgow in July 2025, a major international gathering for gravitational wave researchers. Behind the headlines and records, this event is a reminder of just how much we still don't know. Why do these ultra-heavy black holes exist? How do they spin so fast? What else might be lurking in the data, waiting to be uncovered by better algorithms or sharper minds? The instruments we use to measure these waves are themselves marvels of engineering. LIGO, for example, can detect a distortion in space-time equivalent to changing the distance between Earth and the nearest star by less than the width of a human hair. And yet, that's exactly what's required to capture these cosmic whispers. Sophie Binney, a researcher at Caltech, put it best. This event pushed every limit we have. From technology to theory, it exposed the edges of our understanding and showed us where we need to go next, because somewhere out there, black holes are still colliding, still spinning, still sending out waves that stretch the universe itself, and we're just beginning to hear them, torn space-time echoing across the void, waiting for us to listen.
Teeny tiny black holes capable of hollowing out entire planets might be tunneling through objects on Earth right at this moment. Could those earthly objects include your own body? Very likely. The trick is, in theory, black holes can have an enormous range of size, from those billions of times heavier to the Sun to minuscule far lighter than a paperclip. And those tiny black holes, aka primordial black holes, might be the ones zipping through your arm or leg right at this moment. Now, unfortunately, primordial black holes are so small that we have found no direct evidence of them. But a group of physicists have proposed a creative new approach, looking for their traces in everyday objects. Because although the primordial black holes are incredibly small, they are still large enough to see under a microscope. Now, the chances of finding their traces are still exceedingly small, but on the other hand, it wouldn't take many resources to search for them. Now, what makes primordial black holes so special? They could have formed shortly after the Big Bang, in the extreme heat and density of the early universe. Even cooler, they could be a key part of dark matter, the mysterious substance making up 85% of all the matter in the universe. Unlike black holes that form from collapsing stars or gas clouds, primordial black holes are likely to have originated from extremely dense pockets of subatomic particles, extremely small pieces of matter smaller than atoms, like protons, neutrons, or electrons, in the universe's first moments. These tiny black holes could be as heavy as mountains, but no larger than a hydrogen atom. This combination of high mass and small size makes them incredibly hard to detect. Luckily, to help narrow the search, the researchers made some calculations to predict what signs primordial black holes might leave behind. And one intriguing possibility is that planets or asteroids might capture these black holes, which could then hollow out the insides of these objects. And then, if a planet or asteroid has a liquid core, a captured black hole might absorb the core material, which is denser than the outer layers. After consuming the core, the black hole might escape after a collision or impact shakes it loose. The result could be a hollowed-out planetary shell. Now, if the object is small, about 1/10 the size of Earth, it might remain intact long enough for astronomers to spot it. But larger, hollowed-out planets would collapse under their own weight. This offers another way to search for primordial black holes. If a small planet or moon has a much lower density than expected, it could be a sign that it's hollow and carved out by a black hole. Now, we might not have to search space for clues. Researchers have also figured out what would happen if a primordial black hole were to pass through an object here on Earth. For example, a black hole weighing about a ton could carve a tunnel through an object, leaving an opening about 700 times thinner than a human hair. The coolest thing, though? If something moves faster than the speed of sound through a material, the material's molecules don't have time to react, and the material doesn't rip. It's like the difference between throwing a rock at a window, which shatters it, and shooting a bullet through it, which just leaves a clean hole. Scientists could examine billion-year-old rocks and even structures a few hundred years old for signs of these microscopic pathways. Of course, there's a catch. The odds of finding such a tunnel are very low. According to the researchers' calculations, there's only a 1/10,000th of a chance that a primordial black hole would pass through any specific billion-year-old rock. Even so, the simplicity of the test makes it worth trying. Now, let's talk about the risk to you or your dog if you're ever hit by a primordial black hole. First, let's be clear. The chances of this happening during your lifetime or your dog's are astronomically small. But if it did happen, there's no need to panic. Unlike planets or ancient rocks, your body and your dog's body have only a small amount of tension. It seems hard to believe that a primordial black hole could pass through you without you noticing. But here's a comparison. While you're watching this video, hundreds of trillions of neutrinos have passed through your body at the speed of light, and you didn't feel a thing now, did you? These particles also have another name, ghost particles, and that's for a reason. Maybe someday we'll call primordial black holes ghost black holes. Even though now all of this might sound like pure speculation, studies like these are important. Many ideas that once seemed far-fetched are now accepted parts of science. Creative thinking is necessary to solve some of the biggest mysteries in physics, like the true nature of dark matter, for example. The smartest people in the world have been trying to solve such problems for 80 years without success. So we don't just need minor changes to existing ideas. We need a completely new way of thinking. Now, back on the topic of black holes, astronomers have found a lightweight black hole that's puzzling scientists. The thing is, there's a noticeable lack of black holes between about 2 and 5 times the Sun's mass. Scientists don't know if these smaller black holes are just difficult to detect or if they're genuinely rare. Well, the new discovery might help solve the mystery. This black hole sits right in the middle of that size gap, with a mass of about 3.5 times that of the Sun. Researchers spotted it thanks to its companion, a large red giant star about 5,800 light-years away from Earth. The star, while only 2.5 times as heavy as the Sun, is about 13 times larger and shines 100 times brighter. Astronauts made the discovery using data from the European Space Agency's Gaia spacecraft, which maps the movements of over 1 billion stars in the galaxy. Gaia is really good at tracking stars' 2D motion, which is side to side and up and down. But scientists needed ground-based telescopes to measure how the red giant was moving toward or away from Earth. And their observations revealed something surprising. 2 objects were moving in a wide, nearly circular orbit around each other. And that orbit raised questions. The black hole must have formed because of a supernova, an insanely bright explosion of a star. The star would have lost a lot of its mass very quickly. Such a dramatic weight loss should have disrupted the orbit. It's a basic rule in orbital mechanics. If a binary system loses half its mass, the 2 objects should fly apart. And even if the mass loss wasn't quite that extreme in this case, it should have resulted in a stretched-out oval-shaped orbit, not the almost circular one we can observe. Another challenge to the theory is how supernova explosions behave. They aren't always perfectly even. If the explosion was lopsided, the leftover black hole could have been thrown off course, which would have separated it from its companion star. This might explain why we spot so many small black holes. Most could be wandering the galaxy alone, invisible and unnoticed. That's why the discovery of this binary system is so intriguing. There's also another possible explanation. The black hole and the red giant might have originally been a triple star system, with 2 massive stars at its center and the red giant orbiting further out. And the black hole we see now might have formed when the 2 central stars merged. It's also possible that the unseen object in the system contains 2 smaller compact objects instead of 1. Now, scientists have a wild theory. What if our entire universe is actually inside a black hole? This is called the black hole cosmology. Some scientists have the idea that our observable universe and everything we see around us might be tucked inside a black hole, which exists inside another parent universe or even multiverse. And then this multiverse could be part of a bigger one, and so on, kind of like a stacking doll. Sounds like pure science fiction, but this is based on some curious facts. When scientists create the timeline of our world, they say that everything started from a singularity. If you kept squeezing a giant ball smaller and smaller, at some point it would get super dense before it crushed. Well, it's hard to imagine, but in space, it's possible to squeeze a crazy amount of mass into a teeny tiny point. This point is called a singularity. The matter gets crushed into an infinitely small space, less than an atom, and it holds all the same mass of everything, while taking basically no volume. Inside this singularity point, things get so intense that the normal rules of physics just stop working. Everything we know, time, space, matter, breaks down, and can't be applied anymore. Basically, what happens from now on is beyond our understanding. So, scientists say that this was the starting point of our world. When the Big Bang happened, it's like this tiny dot with everything inside it expanded to everywhere. This started forming the universe as we know it. And here's the thing. Scientists assume that singularity also exists deep within black holes. General relativity says that a black hole is born when something really big, like a huge star, collapses under its own weight. Gravity gets stronger the bigger the mass is. With a mass of a huge star, tens of times bigger than our Sun, this tiny point would have an unbelievable gravity. It's why it starts sucking in all the stuff around it and curves the fabric of space-time so much it looks like a hole in space. And this would be the center of a black hole. It's a dot where all these things fall into and get crushed into an infinitely dense point. So, could our universe itself be just a little singularity dot inside a huge black hole inside of another universe? Well, that would be wild. So, it's not that easy to compress something so much that it literally warps space-time. You'd need to squeeze it like crazy. If you wanted to make a small black hole, like a human size, you'd need to shrink them down to the size of an atomic nucleus. If you want a black hole the size of a chickpea, you'd have to compress our entire planet to that. But our universe is 99% empty space. There are trillions of miles of just nothingness between the stars. If you were to pack all the matter in the universe together, the result would be surprisingly small. Everything around us, including galaxies, stars, planets, and dust, would only fill about 1 billion cubic light-years. It would be a cube about 1,000 light-years on each side. For comparison, our Milky Way alone is 100,000 light-years in size. That's how sparse the universe is. But at this density, it would also be very, very massive. The resulting mass would likely collapse into a black hole. And here's the wildest part. The resulting black hole would be roughly the same size as the universe itself. It would also have the same mass and energy, as well as the same average density. The size or radius of the black hole grows together with its mass. The more stuff it eats, the bigger it is. But the density works the other way around. The black hole gets less dense as it grows. For a size that big of our entire world, it would be pretty sparse as well. And it's not the only coincidence. We have this thing called the Hubble radius, also known as the cosmological event horizon. If we imagine our observable universe as a giant bubble, then think of its edge like the farthest part of the universe we can see. When you stand in a field and look around, trying to see as far as you can, your eyes will draw a circle. This is like that. There might be more beyond that point, but we'll never know. Beyond this horizon, the light from distant parts of the universe will never reach us. That's because light travels at a certain speed, and the space between us and those regions is expanding too quickly. It's like running towards something while super strong winds try to blow you away. Until we stay on Earth, we're cut off from those far-off corners forever. The black holes have something eerily similar called an event horizon, or the Schwarzschild radius. This is the point of no return. This is the imaginary line that's often depicted as a light contour around the black holes. Anything crossing an event horizon, falling inside, is lost forever. No light, no matter, no information can escape from there. Black holes' gravity is way too strong, so they're perfect space vacuum cleaners. And as we mentioned before, if we create a black hole the size of the universe, they would have the same mass and the same event horizon radius. Now, while some scientists think this could just be random coincidences, others believe it's a clue that our universe might actually be inside a black hole. The theory also suggests that our universe might not be the only one. It could exist in one of many black holes scattered throughout a large multiverse. In this crazy model, each one of them, both in our world and our parent world, could lead to its own universe, with its own set of physical laws and structures. Now that would be some weird chain. There's this theory that says that universes could be born inside of black holes, sort of. It's called the Einstein-Cartan theory. This idea talks about singularity as well, but in a different way. It says that instead of collapsing into an infinitely dense dot, the matter might create a wormhole. This is like a tunnel through space and time. This wormhole, also known as an Einstein-Rosen bridge, could connect two different places of our universe. In that case, one side of the tunnel is the black hole, and on the other side, there would be a whole new universe forming. So it could work like a teleport. As soon as you pass the event horizon, you travel to the new world. But in that case, there should be an exit. Some scientists made it up and called it a white hole. It doesn't literally exist, not as far as we know, but it could be possible somewhere on the other side. It would serve as an exit of a wormhole, an area where matter is always ejected instead of pulled in. So it's like you can't throw anything in there, it would get expelled immediately. That's all purely hypothetical, of course. All this stuff fits well into the concept of the Big Bounce. This idea says that instead of our universe beginning with a singular Big Bang, it bounced from a previous state of collapse. Remember the squeezed ball analogy? Well, maybe there used to be another universe ball that got super compressed to a minimum size before rebounding and expanding again. So instead of a universe born from nothing, we might live in one that's a cosmic recycling of another. There's also another version of this theory, sometimes called shockwave cosmology. The idea says that the Big Bang could have been caused by a boom inside a black hole, and this could create the expanding universe we see today. As the universe expands and the matter density decreases, the black hole would eventually transform into a white hole, the reverse of a black hole, where matter is expelled instead of pulled in. But even though we have all these interesting connections, they're not evidence. There are no experiments or observations that could prove or disprove these wild theories. So they all remain speculation for now. But at least it's fun to speculate.
Scientists have thought for a long time that really huge black holes, those called supermassive black holes, sit in the middle of all big galaxies. But for some reason, try as they might, they couldn't find one in a galaxy called the Southern Pinwheel Galaxy, aka Messier 83, or M83, a spiral-shaped galaxy about 15 million light-years away from us. Still, researchers were sure it would be there. That was super confusing. And now, the super powerful James Webb Space Telescope might have found a clue that there really is a supermassive black hole hiding in the middle of M83. Supermassive black holes eat up huge amounts of gas and dust, which makes them glow super bright. M83 didn't seem to shine, but could this glow be hidden by thick clouds of dust? Indeed, James Webb's amazing cameras have spotted clumps of special ionized gas that show up when a black hole is doing its thing, gobbling matter. So basically, the black hole could be playing hide-and-seek with us, and JWST might have just helped us figure out this long-standing mystery. So what exactly did scientists see? It was a glowing light coming from neon gas that needs a huge amount of energy, much more than what normal stars can make. This glow is a strong clue of a hidden active galactic nucleus. Even powerful star explosions, called supernovas, don't give off enough energy to make this kind of light. So, a supermassive black hole seems like the most likely reason. On the other hand, it's not the only possible reason. The glow might also come from shockwaves moving through the gas between stars, called the interstellar medium. To figure it out, scientists are going to take an even closer look using other powerful space tools like the Hubble Space Telescope, ALMA, and the Very Large Telescope. At the same time, this discovery shows how amazing the James Webb Space Telescope is. Apparently, it can find things in space that were safely hidden from our eyes before. Another example is an impossible black hole it helped to detect. On second thought, this discovery might not be as astonishing as it seemed at first. Let's figure out this mystery together. The thing is, astronomers thought they had found a super hungry black hole that was eating stuff 40 times faster than it should. And that was something that didn't make sense with the existing laws of physics. That black hole, called LID 568, was spotted with the help of the James Webb Space Telescope. It was from the early days of the universe, having formed just 1.5 billion years after the Big Bang. So, at first, it looked like the ravenous black hole was eating way too much and way too fast. That would have made it grow really big really quickly, which was surprising for such an early time in the universe. But now, after looking again with the Webb telescope, scientists realized they had been wrong all this time. The black hole hasn't been breaking the rules at all. What actually happened was that thick dust got in the way and made it look like it was eating more than it really was. Here's how black holes normally work. When stuff falls into them, it gets super hot and shines brightly. There's a rule called the Eddington limit, which tells us that the most a black hole can eat is based on how big it is. If a black hole tries to eat more, the light it gives off pushes the stuff away, so it can't eat anymore. Some black holes can eat a little more than this rule says. This is called super Eddington accretion, but not as much as 40 times. And the first guess said that LID 568 was doing just that, breaking this limit in a big way. And then, the new study, published in April 2025, showed that the black hole was actually eating at a normal rate. The mistake came from not seeing clearly because of all the dust in space. It blocks and scatters light, making it harder for us to see the black hole clearly. So, in the end, our hungry friend turned out to be not so hungry and pretty normal. Kinda disappointing, right? Scientists say that if a black hole is hidden by dust, like LID 568, you have to fix the light measurements for the dust to get the right size for the black hole. If you don't do that, you might get the wrong number for how big the black hole is, which also messes up the calculation for the Eddington limit. In their study, the team measured the black hole size using infrared light. This light is not blocked by dust as much as regular light, which is what scientists usually use. Thanks to this, they found out that the black hole was almost 1 billion times bigger than the Sun, and about 40 times bigger than the old guess. With this new, bigger size, they could fix the calculation for the Eddington limit, which made it clear that the black hole wasn't as hungry and bizarre as they thought. So, its feeding habits don't mean it's a super huge black hole growing really fast. Scientists have known that dust can mess up measurements of black holes, but they haven't always been good at fixing it when studying galaxies far away. This means that other black holes might have also been measured incorrectly, and people might have misunderstood them. The team's new way of measuring could help scientists learn more about these black holes that are hidden by dust in galaxies, especially the little red dots galaxies discovered with the James Webb Space Telescope. When scientists look at the first pictures of those faraway parts of the universe, they found something totally new: a bunch of tiny, super red galaxies. They named them the little red dots. There are hundreds of them. These dots only show up during a short time in the universe's history, when the universe was about 1 billion years old. And these little red dots are super confusing. They kind of look like two totally different things: really heavy galaxies packed with stars, or modestly sized galaxies with a supermassive black hole in the middle. But one thing is clear: the typical red dot galaxy is tiny, only about 2% the size of our home Milky Way galaxy, and some are even smaller. So, what makes them shine? There are two main ideas. One of them claims that each little red dot is filled with a crazy number of stars, up to 100 billion, which is about the same number of stars as the Milky Way, even though a red dot is way smaller. Imagine standing in a huge, quiet room. That's like space near our solar system. Now imagine that same room completely jam-packed with the whole population of a very large country. Super crowded. That's what the inside of a little red dot might be like. It could be one of the most crowded places in the universe. Scientists aren't even sure galaxies this packed can really exist. Another idea is that these red dots are small galaxies with a giant black hole in the center. Scientists can spot signs of black holes by looking at how gas swirls around them. It gives off a special kind of light. And in many little red dots, they've seen those signs. Now, here's the strange part. The black holes seem way too big for such tiny galaxies. Usually, a black hole is only a tiny part of a galaxy's weight, about 0.1%. But in some of these dots, the black hole might be almost as heavy as the whole galaxy. That's really unusual, so scientists call those monsters overmassive black holes. And there's one more mystery. Normal black holes give off X-rays, and these ones don't. Even when scientists use special telescopes to look for X-rays, they couldn't find any. It's like these black holes are playing hide and seek, and we don't have the necessary means to find them yet. Astronomers have discovered the most massive stellar black hole ever spotted in our home Milky Way galaxy. This newly found space monster is 33 times bigger than the Sun and sits 2,000 light-years away from us. Until recently, the largest stellar black hole found residing in our galaxy has been around 20 times as big as our star in terms of mass. As for the average stellar mass black hole, it's usually about 10 times as hefty as the Sun. Scientists from the European Southern Observatory's Gaia mission spotted the giant black hole after a star started to wobble while orbiting in that area. The black hole got the name of Gaia BH3. The proximity of this space object to Earth makes it the second closest black hole to our planet ever discovered. The nearest one is called Gaia BH1. It's hanging out around 1,560 light-years away from us. This uncomfortably close neighbor has a mass of about 9.6 times that of the Sun. It means that it's way smaller than the newly found black hole. Gaia BH3 is located in the Agila constellation. From Earth, it seems to have the shape of an eagle. Interestingly, astronomers didn't expect to find a high-mass black hole lurking so relatively close to Earth and remaining undetected for so long. Okay, we can probably admit that this stellar black hole is just a small fry compared to supermassive black holes like the one that dominates the center of the Milky Way. I'm talking about Sagittarius A star. This space giant has a mass of 4.2 million times that of the Sun. While a stellar black hole forms when a star collapses, supermassive black giants have their own ways of seeing the light of day. They are usually the result of mergers of progressively larger and larger black holes. We'll talk about that later. First, let's speak a bit more about how stellar black holes form. When stars near the end of their lives, they typically inflate, lose a lot of mass, and cool to form what we know as white dwarfs. Such massive stellar black holes as Gaia BH3 are believed to form when a star doesn't contain heavy elements and loses not so much mass over its lifetime. Such stars are called metal poor. Afterward, instead of cooling into a white dwarf, this star collapses into a black hole. The companion of Gaia BH3 is a very metal-poor star. It suggests that the star that collapsed and formed BH3 was metal-poor too. Astronomers know of about 50 stellar black holes in the Milky Way. Some black holes are larger than others. You see, the universe is filled with black holes. Some of them are sprinkled randomly throughout galaxies. Others, those giants we know as supermassive black holes, sit at the center of galaxies. While stellar black holes are usually just a few times bigger than the Sun, such space monsters can weigh from 1 million to 1 billion solar masses. But even though they're so much heavier than our star, they're packed into a relatively small area. On a cosmic scale, of course. the size of our solar system or so. Some astronomers think supermassive black holes could form by several stars colliding and collapsing at once, while other experts state that such space objects might have started growing several billion years ago. At first, a small seed appears somewhere out there in space, which then gradually increases in mass to form a black hole. This seed does it through the process of accretion, which basically means gathering more and more matter around itself. Besides the absence of any precise information about the formation of black holes, there's also the black hole information paradox. If a black hole has some mass, and as we know, these spaced objects have a lot of it, then, according to the first law of thermodynamics, it should have a temperature. And according to the second law of thermodynamics, it should also radiate heat. Stephen Hawking showed that black holes are supposed to emit radiation too. These days, this kind of radiation is called Hawking radiation. It should form at the boundary of a black hole, but after proving it, Hawking pointed out a paradox. If a black hole is capable of evaporating, some of the information it contains can be lost forever. The problem is that the information contained in thermal radiation emitted by a black hole gets degraded. It doesn't repeat any information about the matter swallowed by a black hole before. Such an irreversible loss of information contradicts one of the basic principles of quantum mechanics. Physical systems that change over time cannot create or destroy information. It means we must be missing something. Both physicists and mathematicians have tried to come up with different ideas, but they ended with pretty weird results. Some have even claimed that the universe could be holographic. It means that the universe that we know and love is actually the result of some mysterious interactions at the infinitely distant boundary. I told you, black holes are really strange. At the same time, we have definitely found space objects that seem to have the properties of black holes. For example, look at this image of black hole M87 star. It certainly looks like a physical object, but what if black holes don't exist at all? There's an idea that black holes are actually gravastars, a blend of gravity, vacuum, and stars. This theory was first proposed in 2001 by Emil Matola and Pavel O. Mazur. They hypothesized that at one point during the collapse of a large star, intense gravity might transform its matter into a new state. It's similar to what occurs when atoms are cooled to such low energy states that they start acting like a single superatom. When we speak of gravastars, a star might collapse to the point of the event horizon, or the point of no return, and then its matter is transformed into a new state. It exerts enough outward pressure to prevent the star from collapsing into a physics-defying singularity. In gravastars, an ultra-thin, ultra-cold, and ultra-dark indestructible shell surrounds heavily wrapped spacetime. This new form of matter turns out to be very durable, but it's also a bit flexible, like a bubble. So anything that's trapped by the intense gravity of a gravastar and smashed into it gets obliterated and then assimilated into the shell of this bizarre space structure. One of the benefits of the gravastar theory is getting away with those messy paradoxes connected with information and singularities. But even though this idea sounds kinda cool, it doesn't explain the phenomena we observe. And we've definitely observed something that looks like black holes. On the other hand, look at this shadow. It isn't caused by the trapping of light in the event horizon. It's a slightly different phenomenon known as the gravitational redshift. It makes light lose energy when it moves through a region with a powerful gravitational field. So, potentially, it could be a gravastar. When the light emitted from the regions close to the alternative objects reaches our telescopes, most of its energy is already lost to the gravitational field, which causes the appearance of this shadow. And still, like with black holes, things get complicated when you add rotation to the equation. Many experts are sure that gravastars would not be able to remain stable during rotation. But wait, it gets even more bizarre. There are suggestions that the insides of gravastars could contain a series of thicker shells. Those are known as nestars, something like a matryoshka doll. Of course, these theories aren't perfect yet. Astronomers still have a lot of work trying to build functioning models. There's also a chance that both black holes and gravastars exist. But then, we've got another problem on our hands. How can we distinguish between the two? Some theories suggest that these different kinds of space objects should also emit very different gravitational radiation. It could allow us to figure out whether we're looking at a gravastar or a traditional black hole.
Brace yourself. We might be living in a ginormous black hole. The James Webb Space Telescope has been sending back some pretty crazy stuff. It has looked at a bunch of really far away galaxies, those super old ones from the early universe. And guess what? Most of them are spinning in the same direction. To be precise, around 2/3 spin clockwise, and only 1/3 spin the other way. But if the universe was totally random, you'd expect it to be 50-50, half going one way, half the other. And that's not what's happening. So now, some scientists are wondering if this means the universe isn't as random as we thought. And there's also this wild theory that everything we see might actually be inside a giant black hole. Now, scientists aren't totally sure why this is happening, but there are two main ideas floating around. One possible explanation is that the universe was actually born spinning. The most shocking thing here is that his idea lines up with a theory called black hole cosmology, aka Schwarzschild cosmology, which basically says that our entire universe might be sitting inside a giant black hole. Like, we could literally be living in the middle of one, hidden inside a much bigger parent universe. This idea was first brought up when some smart folks noticed that the edge of a black hole, called the event horizon, aka the point where not even light can escape, might actually line up with the edge of our observable universe. So, the horizon we see when we look into space could be the same kind of boundary as the one surrounding a black hole. If that's true, then every black hole in our universe could actually be hiding a whole other universe inside it, a so-called baby universe. We just can't see or reach them because of that same event horizon. It's like a one-way door. Stuff can go in, but no info or light can come out. And even if something is happening inside, it remains completely invisible to us. So instead of the Big Bang starting from nothing, maybe it came from inside a black hole in another universe. When a massive star dies, its core collapses and forms a black hole. Normally, we think everything gets crushed into a super tiny point called a singularity. But there's another theory. When things get that dense, something called torsion, which is a twist caused by spinning particles, kicks in. And when that twisting force gets strong enough, it stops the collapse and causes a massive bounce. A similar bounce might have started our universe. The insane gravity at that moment could have created tons of particles, added mass, and fueled this huge expansion. So instead of a big bang out of nowhere, we might have had a big bounce from inside a black hole. That would also explain why our universe looks so smooth and flat today. The theory goes even further. Thanks to torsion, every black hole might actually create a new baby universe inside it. And then, instead of black holes being dead ends, they might be wormholes, kind of like tunnels, connecting our universe to another one. And when stuff falls into a black hole in our universe, it might be popping out into a new universe on the other side. And in that new universe, our black hole would show up as a white hole, the exact opposite of a black hole. You can't go into it from the outside, but things can come out of it. But let's talk a bit more about those new James Webb findings. If our universe turns out to have a preferred axis, like a cosmic direction in which things tend to spin, that could indeed mean that our universe was born inside a black hole from another universe. You see, black holes form from stars, galaxy centers, or even tight star clusters called globular clusters. All of those things rotate, so when a black hole spins, any universe it creates inside might inherit that spin. Basically, the axis of rotation from the black hole could become the cosmic spin direction in the baby universe. However, there's another explanation for why the Webb telescope has seen so many galaxies rotating in one direction. And this explanation is that the Milky Way's own rotation could have caused it.
If you've ever wondered about what a black hole consists of, you're in the right place at the right time. I bet you've heard of this first one, the event horizon, and it's exactly what makes a black hole. Well, black. We could probably think of the event horizon as the boundary of no return. Once you cross the event horizon, the velocity you need to escape the clutches of the black hole is already higher than the speed of light. So, whatever passes the event horizon, be it light or any object, is doomed to stay inside. And since light can't get out from behind the event horizon, black holes neither emit nor reflect it. Nothing about what happens to them can reach an outside observer. But wait, then how did we get these beautiful photos of black holes? The thing is, we observe not the black holes themselves, but the light emitted by the matter surrounding them and forming a structure called an accretion disk. That's the main light source of black holes. For example, look at this stellar mass black hole. It's paired with a star and is pulling gas from it. Supermassive black holes do the same, but they munch on stars that stray too close. Eventually, all this stolen gas settles into an insanely hot, bright, and rapidly spinning disk. Matter is working its way from the outer edges of the disk toward its inner sides. Once it reaches the edge, it falls into the event horizon. If you looked at an accretion disk from up close, you'd see that it has a rather funny shape when viewed from some angles. That's because the gravitational field of the black hole warps space-time, the very fabric of the universe, and light travels along curved lines. The clever word for this process is gravitational lensing. The light that comes from the top of the accretion disk behind the black hole seems to form a hump above it. You can notice it in this image, see? And the light from beneath the far side of the disk creates another hump below as it takes a different path. But the coolest thing, if you looked at the disk exactly face on, you wouldn't notice any humps whatsoever. Then we've got the event horizon shadow. This is a dark zone which is around twice as big as the black hole's actual surface. The shadow is created by the combination of two effects. First, the event horizon captures all the light passing through it, and second, the curved space-time around the event horizon causes light to be redirected through gravitational lensing. Let's move on to the next part of the black hole, and it's a photon sphere. Do you see these thin rings of light that appear at the edge of the black hole shadow? They're actually numerous, highly distorted images of the accretion disk. Here, light from the disk orbits the black hole multiple times before escaping. The closer to the black hole, the thinner and fainter the rings are. There's also another visual phenomenon known as Doppler beaming. From most angles, one side of the accretion disk always looks brighter than the other. That's because near the black hole, the disk spins so fast that light streaming from the part of it spinning toward us becomes bluer and brighter, while light from the side of the disk rotating away from us becomes redder and dimmer. Next, you've probably heard that our sun has something known as the corona. Well, the black hole has one too, and it's one of the most extreme environments in the universe. Some scientists claim that powerful magnetic fields threading the inner accretion disk extend out and create a turbulent billion-degree cloud. Particles in the corona hypothetically orbit the black hole at speeds approaching the speed of light. Some experts believe that the corona might be a source of ultra-high energy X-rays, but we still don't know much about them. Plus, these coronas themselves can appear and disappear, following some patterns only they are aware of, which makes them even more mysterious. And finally, according to the theory of general relativity, the center of the black hole contains a point where matter is crushed to infinite density. This point is the final destination of anything falling into the event horizon, and it's called singularity. At the moment, astronomers aren't sure whether it's a physical structure or a purely mathematical one.
The James Webb Space Telescope has recently discovered the oldest black hole ever found. It's an ancient monster as massive as 1.6 million suns, and it's lurking 13 billion years in the past at the center of an infant galaxy. This supermassive black hole appeared a mere 440 million years after the beginning of the universe. But it's just one of the countless black holes that inflated to terrifying scales during the dawn of the cosmos. It's the period about 100 million years after the Big Bang. That's when the young universe started to glow for 1 billion years. This discovery of the universe's oldest black hole can provide astronomers with the answers to some vital questions. For example, how could these space whirlpools balloon in scale so fast after the universe began? Or how did they appear in the first place? You see, black holes in the early universe couldn't grow as quietly and steadily as many modern black holes do. They were bound to experience some peculiar formation and growth. At the same time, closer to the present day, black holes are believed to be born from the collapse of ginormous stars. They grow by munching on gas, dust, stars, and other black holes non-stop. The friction created in the process makes the material, spiraling into a black hole, heat up, and it emits light that can be detected by our telescopes. To spot the oldest black hole, scientists used 2 infrared cameras, the JWST's mid-infrared instrument and near-infrared camera. They used the camera's built-in spectrographs to break down the light it had been recording into its component frequencies. While examining the results, they discovered unusual spikes among certain frequencies. It could only mean that the hot material around a massive black hole was beaming out faint traces of light. One of the most popular explanations for how ancient black holes grew so rapidly is that they appeared after sudden collapses of colossal gas clouds. Or they could form as a result of merges between clumps of stars and black holes. There's also a possibility that some of the oldest black holes could have been seeded by hypothetical primordial black holes. Those are believed to have appeared moments after the universe began, but their existence hasn't been proven yet. In any case, this most recent finding of the ancient black hole is extremely important because the formation of galaxies and the appearance of black holes go hand in hand. Every normal-sized galaxy that we know of has a black hole at its center. But even though such black holes are massive and can weigh millions and billions of solar masses, they are still tiny in comparison with their home galaxies. A supermassive black hole usually reaches less than 1% of the mass of a regular-sized galaxy and has a volume that is billions of times smaller. And still, somehow, supermassive black holes can influence galaxies, controlling the formation of stars for billions of years. The thing is, black holes exert an enormous gravitational pull on their surroundings. Any gas, dust, and stars that come too close to a black hole find themselves trapped. A lot of material crams into the space around the black hole and heats up, because that's what materials do when compressed. Soon, everything around the black hole flattens into a thin disk, which is called the accretion disk, and starts swirling around the black hole. astronomers believe that this process is behind the mysterious relationship between black holes and their host galaxies. It's a connection between the mass of the supermassive black hole and the velocity dispersion of the gas in the galactic core. This cycle also controls the rate of star formation, which is a crucial element of the evolution of galaxies. If this delicately balanced process goes off kilter, the outflows from black holes can get too strong, not only heating the gas in a galaxy, but also removing it altogether. And then, the formation of stars doesn't simply slow down, it stops completely. Major galactic merger events can lead to such dramatic consequences because too much material falls into the central black hole too fast.
A giant star is on the brink of exploding, and clinging to its side is a newborn celestial companion that might not survive its embrace. High in the night sky, nestled in the shoulder of Orion, Betelgeuse, a colossal red supergiant, is nearing the final stage of its short but intense life. This final phase marks the onset of core instability, where the star rapidly fuses heavier elements until its core collapses. It's a star so large that if you placed it at the center of our solar system, it would swallow everything up to Jupiter, and it's unstable. One day, not too long from now, in astronomical terms, it's expected to erupt in a violent supernova, visible from Earth. But Betelgeuse isn't dying alone. Astronomers have uncovered a hidden partner orbiting dangerously close, a faint bluish star that hasn't yet matured. This companion isn't just tagging along, it's cutting straight through the outer layers of Betelgeuse's puffed-up atmosphere, disturbing its outer material and likely affecting mass loss and surface turbulence. The interaction turns the region into a glowing, ionized swirl of gas. This is no gentle partnership. It's more like a firefly waltzing through a furnace. The discovery reshapes what we thought we knew about Betelgeuse. For years, scientists were puzzled by its irregular flickers, mysterious patterns of dimming and brightening that defied easy explanation. One particularly strange episode occurred in 2019, when the star's brightness dipped so dramatically that some believed it might explode at any moment. The culprit, it turned out, was a massive cloud of stellar burp, gas and dust spewed from Betelgeuse itself that briefly veiled its surface. But the repeating fluctuations, they hinted at something else, something orbiting nearby. That companion was recently spotted using the ultra-precise imaging power of the Gemini North Telescope in Hawaii. The telescope pierced through Betelgeuse's searing glare and identified the companion, confirming what had long been suspected. Betelgeuse is part of a binary star system. Some astronomers informally call this companion the Beetle Buddy, though its technical nature is still being studied. The two stars make for an odd couple. Betelgeuse is bloated, aged, and on the edge of detonation. Its companion is compact and young. So young, in fact, it hasn't even begun fusing hydrogen in its core, the defining trait of a mature star. It's like watching an elderly titan lumbering toward collapse while a toddler clings to its arm, unaware of the coming doom. Every 5 or 6 years, this smaller star completes a close elliptical orbit around Betelgeuse. And in doing so, it disturbs the supergiant's outer layers, adding heat and energy that may be partly responsible for its erratic brightness. Think of it as stirring a pot that's already boiling over. The implications are huge. This orbiting companion helps explain years of unpredictable behavior. It also provides a rare look at what happens when a massive star lives its final days with a partner locked in a fatal dance. Because make no mistake, this is not a story with a happy ending. The baby star is in mortal danger. 2 possible fates await it. If Betelgeuse goes supernova while the companion is still near, the resulting explosion will likely obliterate it, incinerated or ejected at high velocity into deep space. If instead the red supergiant lives a few more millennia, the companion may spiral inward and be absorbed, vanishing into the belly of its massive host. Either way, the clock is ticking. To appreciate just how dramatic this is, remember, Betelgeuse is around 10 million years old. ancient by human standards, but fairly young for a star. Yet because it's so massive, its life burns out fast. While stars like our Sun enjoy stable lifespans of 10 billion years or more, giants like Betelgeuse live fast and die young, their sheer mass accelerating every nuclear process. What will that look like from Earth? When Betelgeuse finally erupts, it will outshine every other star in the sky, possibly even visible in daylight. It won't harm us. It's too far away for that, but it will give humanity front row seats to a spectacle we haven't seen since SN 1987A or even the Crab Nebula supernova recorded in 1054. And all the while, that quiet little companion continues its doomed loop, threading through the fringes of a star that's tearing itself apart. There's something poetic, even tragic, about their cosmic relationship. One is aging, bloated, unstable. The other is young, barely formed, just beginning to shine, but already marked for destruction. Together, they remind us that the universe is full of unlikely pairs, wild physics, and relentless motion. And sometimes, stars die not alone in the dark, but clasping another in a final fatal orbit.
Picture a silent ember drifting toward the sun, moving so quickly that no gravity well in our system can bind it. That ember, provisionally tagged 3I Atlas, appeared in late June when the Atlas Hazard Survey cameras in Hawaii and South Africa logged a faint, fast intruder. Initial orbital fits showed an eccentricity greater than 1, the mathematical stamp of an origin beyond the sun's reach. We have met only 2 such emissaries before, 1I Oumuamua in 2017 and 2I Borisov in 2019. Now a third arrives, tugging at our curiosity and our instruments in equal measure. The object's present speed is almost 70 kilometers per second, enough to span New York to London in 90 seconds. Backtracing the path leads toward the constellation Lyra. Forward projection shows a swing past Mars on 3rd October 2025, a solar perihelion 20 days later at twice Earth's distance, and final escape by early 2026. Earth stays on the sun's far side throughout, so the risk ledger reads 0. The intrigue ledger, however, is packed. Composition sits at the top of the to-do list. A comet would sprout a gaseous veil as ice evaporates, yet deep imaging has yet to reveal any coma. An asteroid would follow purely gravitational curves, yet a whisper of extra thrust may lurk in the astrometry. The James Webb Space Telescope can cut through reflected sunlight and sample the infrared glow for water, carbon monoxide, or exotic minerals. If the spectrum comes back featureless or metallic, theories multiply. Brightness fuels the puzzle. Even with a modest albedo, the observed flux implies a body several kilometers wide, far larger than Oumuamua, whose size was measured in hundreds of meters. A highly reflective hull could achieve the same luminosity with far less mass, a possibility that keeps technosignature specialists awake. Professor Avi Loeb, already known for suggesting an artificial origin for Oumuamua, is lobbying for continuous JWST tracking to test for non-gravitational acceleration. A persistent drift unaccounted for by gravity would demand explanations that push against the boundaries of conventional astrophysics. Statistics pose the second riddle. For centuries, astronomy recorded 0 interstellar passers-by. Now we count 3 in 8 years. Better sky coverage explains part of the surge, yet simulations indicate the detection rate is still high. Either the density of galactic debris is underestimated, or transient swarms are sweeping the sun's neighborhood. The Vera C. Rubin Observatory, starting full operations next year, will clarify the odds by mapping every moving speck down to faint magnitudes every few nights. Structure forms the third unknown. Light curve monitoring can reveal whether 3I spins like a platter, a spindle, or a rubble pile loosely bound by microgravity. Oumuamua's flattened shape and unexplained kick remain controversial. A repeat would strengthen calls for new physics or new engineering. Rapid tumbling might indicate past collisions, freshly exposed ice, or even deliberate attitude control. That opportunity extends well beyond the object itself. Each interstellar visitor carries isotopic fingerprints of the chemistry that shaped alien worlds. Sampling those fingerprints, even remotely, refines models of planet formation, volatile delivery, and the migration histories of giant planets. In a decade, robotic missions may be fast enough to intercept such bodies. Today, we practice with photons. Time is tight. By September 2025, the object will vanish into solar glare. By the time it re-emerges, the outbound leg will dim below major telescope thresholds. Roughly 5 months remain for the most ambitious observations. Teams are coordinating radar pings, ultraviolet spectra, and high-cadence photometry to squeeze every bit of information from the fleeting visitor. Why should the broader public care? Because 3I Atlas is a tangible reminder that our solar system is not an island, but a crossroads. Somewhere an unknown star flung this body into the dark, perhaps through a near miss with a giant planet, perhaps through a cataclysmic collapse of a binary pair. After wandering for millions of years, it has brushed past our doorstep, offering a message in a bottle. The galaxy is bustling, and we are part of that bustle. Whether the newcomer proves to be ice, rock, metal, or something unprecedented, its brief appearance renews a sense of frontier. Sky surveys sharpen, theories adapt, curiosity deepens. The next discovery may come sooner than anyone expects, and when it does, the groundwork laid today will allow us to read its story more clearly. For now, astronomers chase a streak of light across CCD frames, and every clear night might deliver a clue that rewrites chapters on planetary science, or adds a footnote to the search for artifacts among the stars. In either case, the sky is not done surprising us. Origin scenarios abound. Some simulations eject 3I from a nascent planetary system after a close brush with a giant planet, while others invoke a crowded stellar nursery where passing stars fling debris across interstellar lanes. Whatever the trigger, the body has drifted for perhaps tens of millions of years, carrying the isotopic signature of an alien chemistry lab. Radio arrays will also listen for narrow-band emissions, more out of thoroughness than expectation. After Oumuamua, techno-signature protocols are standard. Scan, archive, move on, unless a signal repeats. Looking ahead, Rubin's legacy survey of space and time should uncover several interstellar objects every year, identified early enough to permit rapid robotic flybys. Concepts under study at multiple space agencies outline launch-on-alert missions that could sample surface dust or even return grains to Earth. Each discovery thus acts as rehearsal for the day we chase one down in person. Whether the outcome is ordinary or transformative, the chase itself pushes instruments, sharpens global teamwork, and teaches the next generation to aim beyond yesterday's limits.